Hi everyone, this is our video submission to the Simulink Student Challenge 2024 presented by Marc, Isaac, Taken Yu, Liu Hongwei, and me myself, Tan Xueqi. We'll be introducing our MEMS IMR thermal sensor created using MATLAB Simulink. The background of our project is thermal sensor detect heat emitted by objects, especially humans. It is used in common applications include motion-activated security lighting, energy-efficient system, and temperature-sensitive industrial lighting. Nowadays, there's a rising demand for energy saving in automated solutions has driven advancement in thermal sensor technology. Our project aims to reduce energy waste, improve safety, and provide modern adaptive lighting solutions. The objective of our project are develop an intelligent human presence detection using MEMS IR thermal sensor by temperature or heat-based detection, and enhance energy efficiency by activation only when presence of human is detected, and improve user convenience and safety through automation.
This Simulink circuit models the thermal response of a MEMS infrared sensor designed to detect human presence through radiative heat transfer. The system captures heat from a nearby human body and converts it into measurable voltage output using the seeback effect. Let's walk through the circuit step by step. The simulation begins with a controlled heat flow rate source representing the heat flux emitted by a human body. This heat flux mimics the radiative heat transfer from the human. The input to this block allows dynamic variation in heat flux over time, simulating the presence and absence of a human. The heat flux from the human body is transferred to the thermal mass, which represents the silicon material of the MEMS sensor. The thermal mass is modeled as a block of single crystal silicon with the following physical properties. In fact, here are all of the parameters used in this Simulink design. This thermal mass captures the energy absorbed through radiative and convective heat transfer mechanisms. To account for thermal energy loss, radiative, convective, and conductive heat transfer mechanisms are used to simulate the heat dissipation from the thermal mass. Next, the temperature is then measured using a temperature sensor which records the temperature difference of that point in the circuit. This paired with the gain block simulates the seeback effect of real-life thermal sensors. This gain block contains the seeback coefficient for silicon relative to platinum, which is 440 microvolts per Kelvin. This converts the temperature difference reading into voltage. From here, the physical signal is converted into a voltage signal within the electrical side of SimScape. This electrical signal is then read by a voltage sensor. In summary, the circuit produces three key outputs, which is the heat flux supplied to the thermal mass, the temperature change, and the voltage output, which are all sent to this scope here, which can be viewed to observe the simulation results. Now, let us see the results produced when a heat flux of 105 watts per meter squared is being emitted by a human. As you can see, the flux increases, the temperature change is detected, hence a voltage is produced. Now, how about when a heat flux of 210 watts per meter squared? This is double. Perhaps the human has a higher body temperature at this time. The voltage produced here is around twice the amount from earlier, implying that the temperature change and voltage produced is positively proportional to each other.
The analysis on the outcomes of the MEMS thermal sensor simulation demonstrate its effectiveness in detecting temperature differences in a dynamic environment. The sensor's design mimics thermocouple behavior, where a rise in temperature results in a proportional increase in voltage. By varying input parameters using the PS step block, the simulation showed significant changes in voltage output, validating the sensor's sensitivity. For example, when a human enters the room, the sensor detects the temperature increase, leading to a voltage rise, which can be used to trigger the lights. Conversely, when the human leaves, the temperature drops. The sensor output decreases, turning the lights off. These results align with theoretical expectations and confirm the sensor's capability to dynamically respond to real-time temperature changes. Now, moving on to the discussions on the outcome, these findings highlight the sensor's potential for application in automated lighting systems and energy-efficient building management. The ability to sense heat flux changes caused by human presence makes it ideal for environments requiring responsive lighting systems. However, the current simulation could be improved by incorporating external factors such as ambient airflow or sensor placement optimization to better represent real-world conditions. Addressing this limitation would further enhance the sensor's accuracy and applicability, ensuring its effectiveness in practical implementations.
To conclude, we have successfully created a model of our small-scale MEMS thermal sensor using MATLAB Simulink. We believe that the model that we have created could be applied to various applications that would significantly improve our daily lives as well as enhance energy saving. Thank you.